Let's make a 10 minutes very sharp prompt coffee break. Yes, hold on.
Okay.
Let me see. Let me just pause the recording. Start the recording. The meeting is going, so it should be fine. Well, you should probably sit next to this laptop and make sure that it's capturing the part of the screen, the part of the Blackboard that Ella is working on. It's just occasionally you have to tilt it left and right.
Right now it's got everything except the last part.
No. It's gotten.
Yeah, it does pretty well down there.
Oh, you're right. It's got so this corner.
You can't see it, right?
So I think that this panel is
Yeah, it's
outside.
just the last panel.
Yeah, I mean,
Right.
that's
So
hard
if
to
you don't write
No,
here,
that's hard to use. It's hard to use anyway. Yeah.
okay. So maybe you don't need to.
Okay. So
Yes. Giovanni is chairman.
Okay, so Al Mueller will talk now, and please.
thank you. Thank you. So what I wanted to talk, what we're going to talk about is diffraction. I had the advantage of, I just gave this talk last Friday afternoon at Brookhaven, so I had a little bit of practice. So this is it's very simple compared to what Yuri was talking about. So this is really very, very simple stuff. This is a discussion of diffraction and deep inelastic scattering. And in particular, the result that it works with Stefan Meunier. We were inspired by this by a set of results on ancestors in statistical physics, which had recently come out by Derrida and Montchamp. And in going through that, we recognized that what they were doing looked an awful lot like diffraction. They give a rule for how likely it is if you measure some particles after a long time in a branching random walk. They give a rule for the probability of finding the first common ancestor at a certain time. And it's a simple analytic result. And we are now, what we did is to try and reproduce that for diffractive scattering, and we found an identical simple analytic result for the, not for the value of the diffractive cross-section, but for the relative probabilities of different gap sizes. So the function of the gap size in large mass diffractive production, there's a simple analytic result. And the argument is very, very, very simple, but it requires a bit of background. So almost the whole talk is going to be background. For some of you, I'll be boring you because you already know a fair amount of this. For others of you who don't have a background in branching random walks, I hope this will be sufficient to make it at least plausible. So I say much of the talk is going to be background material. So I want to talk about, begin by simply, see, there's this tremendous analogy between many processes in statistical physics and QCD. For example, a branching random walk, the mean field picture of a branching random walk is the BFK-L equation. Dipole evolution at the stochastic level is a branching random walk. And so there are tremendously strong analogies, and it's easier to explain a number of the ideas in the context of a branching random walk, carry them directly over to dipoles and QCD, and then give a very simple argument for the probability of gap sizes in diffractive electron nucleus scattering in terms of just a physical picture. Now, what I'm going to present is just going to be a physical argument for an answer. Stefan then solved numerically the Kochetkov-Levin equation and verified, for at least for large rapidities, verified the analytic form that we'll find in the Kochetkov-Levin equation. Kochetkov-Levin equation is it's like a BK equation, but it's for diffraction. It's a bit more complicated, but apparently numerically it's not so hard to solve. hey, Stefan, solve this, and I won't, that discussion is in the paper. I won't go through that. But that's sort of they say because our discussion is in the end very intuitive, the numerical simulations were important to make sure that we hadn't been fooling ourselves in our overall understanding. Okay, branching random walk. A branching random walk, we started in just one-dimensional branching random walk. We have a line, X line, and say at the origin here, there's a particle. And then in an interval delta t, what can happen is that we start with say one particle at the origin. And what can happen to that particle over a little bit of time? We can do one of three things. It can just multiply into two particles. So this is a probability, the probability P12 times delta t, or with with another probability, which I won't label. I'll just say it's diffusive. The particle can, from the origin, it can move to the left or to the right. So there's a certain probability. The probability of the distance it goes is always taken to be a Gaussian. It's with a fixed term in the exponential. So it moves in a Gaussian manner with an overall probability, and then a proportional to delta t. And then the third thing it can do, it can just sit and do nothing. So, and this is what the power. So this is multiply, diffuse over a microscopic distance, or I can do nothing. And that must be the rest of this probability. So this is 1 minus P12 minus diffusion probability integrated over the x variable of diffusion. Now that's effectively the same as what happens in a dipole split. So when you have a dipole, the dipole has a probability, quantum mechanical probability of splitting into two dipoles. That's the multiplication. The slight difference is that in the dipole case, the diffusion comes at the same time as the splitting, because the dipole of a certain size splits into two dipoles of two different sizes. Now, here the amount of diffusion is strongly regulated by Gaussian cutoff. In QCD, splitting a dipole split into two very large dipoles is cut off by power. A dipole splitting into two dipoles, one of which is very small, is not cut off. But those very small dipoles, which are very, very common, they play no role in any physical process. And so, in fact, it effectively looks like this. Okay, now I want to use this. I want to use this to give a dual picture of, I'm going to call it scattering. But I'm first going to write down two equations. Even in the statistical case, I'm going to use the word scattering. There's a differential equation closely related to a branching random walk, which is the FKPP equation. I'll tell you how that relation comes in a moment. FKPP equation, and that equation I'll use t, time and x dt. Now I've just explained sort of the idea of the branching random walk, and the equation that's associated with that has also a diffusion term, so it's a d squared t of t and x, dx squared. It has a growth term which corresponds to the multiplication t, and it has something which isn't in this picture so far. Square of t. But I'm going to relate this equation to this picture in just a second. But at the same time, I want to talk about the dipole equation, pK equation, which is a very simple, very similar equation. It now will have a t as a function of a rapidity The constants have been chosen to be 1 here simply by rescaling of what x and t variables are. And say an x01, so this is starting out with a dipole of size x01, and then if you increase the rapidity, what can happen is the dipole at one end of the evolution parent dipole, which can split with a probability alpha over 2 pi squared, and then b squared x2 and x01 squared. I'll draw this picture. I'll draw the pictures below. x02 squared, x12 squared. And there could be a scattering in, say, y and x02. So let me draw that picture. So this is the t here is the dipole, x01, and then scatters sand on a big nucleus. And there's just some generic scattering. And then over here, the dipole splits into a 0, a 1, and a 2. This is the time t equals 0. Here, the time t equals 0 of the scattering. And then, well, we still not getting that quite yet. And the scattering here could be between 0, 2. There could be a scattering y of x1, 2, and that's and then there's the probability conserving part. And then the unitary part. So these equations are very, very similar. This is obviously somewhat simpler. It's one-dimensional. It doesn't have a convolution here, but they're formally they're in the same, it's called the same universality class. If you want a simple discussion of this discussion of the universality class, Stefan Mueller gave a set of lectures in China 3 years ago. They were published in some Chinese journal. I forgot the name of it now. But they're very, very, very nice set of lectures, and he gives a formal proof of the fact that these two equations are the same universality class. Now, this is not so much.
You switched your notations to make sure I understand. You switched your y's and x's in the last term. Is that on purpose? Or
Would you forgive me?
I just want to make sure I follow.
No, you're right, I did. I'll switch many things. Well, I'll do worse than that before.
I forgive you.
Okay. Now, the result I'm after is an interesting result. It dates in the statistical literature. I think it dates back about 40 years ago. I believe it was due to a mathematician at MIT called Henry McKean. And what he did is he relates. Now I'll erase this.
You can use the left panel to assume.
Okay.
Right here.
Okay, let's take the FPP equation. I want to start out with an initial condition. So let's look at FPP. This is a duality, which I'm after. Let's start out at t equals 0. And this is the t, this is the x variable. And at t equals 0, let's imagine the distribution looks like this. It's a step function. T is 1 for all negative values of x, t is 0 for all positive values of x. You're thinking, aha, that's a McGregor-Vedder-Goldman nucleus, right? McGregor-Vedder-Goldman nucleus is essentially have dipoles greater than the inverse MV saturation momentum. The T matrix is 1. If you have dipoles precisely less than the MV inverse MV saturation momentum, it's 0. Now, in the MV case, it's not a real step function, but it's a faster fall off than any of the other rates that happen in the scattering. And so it's effectively the same. So this is like an MV nucleus, but anyway, it is what it is. It's just a step function. As you evolve in time, this thing looks like, well, we know what it looks like. You do an evolution with the FTP equation. And this is 0 now. And then it goes out here someplace. It looks like that. That's all right. And now suppose we take a point x here, and we measure t of t and x. Okay, t of t and x is just the value of this function t after doing the evolution over a certain period of time. And of course, there's some peak point here, x of t. If x is less than that, t will be very close to 1. If t is greater than that, there's a scaling region, then a very, very strongly falling off region at large x. And now this interesting sort of duality is that you can get that by doing another process, a slightly different process. You can start, let's focus on the point, this is generic x, and this is the particular point x, and I'm looking at which I'm not going to use a separate label. This is our point x that we're looking at. So let's again start at t equals 0, like this. That point x. And now, instead of evolving this by FKPP, let me take this point here and let me start to do a branching random walk on it. We'll keep this fixed, this size fixed. I'm just going to do a branching random walk, and then I'll describe the relation between these two. So after doing branching random walk, what happens is that this grows. So the branching random walk, I've erased the picture, it grows near x. It's starting out at a point x with a branching random walk of this one particle here. So I'm really viewing this as like a scattering. I'm saying the probability of the scattering is just the value of this t at point x. I'm now going to treat this as a particle, and as this particle starts to evolve, and so it'll have some big peak over here, and then it'll come down, and then at the end it becomes a little bit wobbly over at the end. Now the statement, and this is going to be the statement of the duality, in this picture, t of x in t is the probability that a descendant of x, so this is the point x we're starting from, a descendant of x after t evolution, time t evolution, so from a descendant is say that one or more descendants of x after t evolution is to the left. X equals 0. This is an exact theorem. It says if you start a branching random walk, but this branching random walk had no unitary index, arbitrarily high, do this branching random walk, then you have to, since it's a probability, it means you have to do this branching random many, many, many times, and then you ask what's the probability that some descendant of this branching random walk came to the left, one or more descendants comes to the left of this point, x equals 0, and that answer, that probability, is given exactly by the solution of the FKPP equation. Well, it's kind of, in one sense, it's trivial. We know it. We know that that was true, and I'll explain why we kind of know it in a second. But in a way, it's also very, very surprising. We have a stochastic process which has no nonlinearity in it whatsoever, but yet one says that a certain probability within that branching random walk is given by the solution of a nonlinear equation. Very surprising. Now, why is this sort of obvious? Well, let's think physically. We've got to make clear we've got to go up on a nucleus, and we've got a dipole. We've got to do high energy dipole scattering. There's two ways of doing it. You could evolve the MV nucleus by the BK equation, and then just scatter the dipole in that evolved equation, and that's just the value of the T that you get here. But obviously, we can do it in another frame. We can let the dipole evolve itself. But the big nucleus is got a lot of substructure to it. You don't have to do stochasticity. There's a self-averaging because the big nucleus is many, many, many nucleons. If you start out and evolve the dipole, that's one object. And whether it's going to split in a certain rapidity or twice that rapidity or 3 times that rapidity is going to vary from event to event. There's going to be gigantic fluctuations in that. And so you have to do a probability. So if you want to calculate the scattering matrix by evolving the dipole, you have to evolve it, take an event, find out what the chances are see, in the McLaren-Vanderbilt case, you evolve the dipole, and then it will scatter on the nucleus. You get an event if some dipole in that evolution has a size bigger than the inverse McLaren-Vanderbilt saturation momentum. If there's no dipole in that evolution, which is bigger than the inverse McLaren-Vanderbilt saturation momentum, it won't scatter. And so you just do many, many different events, and you say, what's the probability of having a dipole whose size in a dipole in the evolution over a rapidity y what's the probability of having a dipole whose size is greater than 1 over the McLaren-Vanderbilt saturation momentum? And so this, in terms of a physics point of view, is almost obvious.
So, sorry, I kind of maybe spaced out at some point. So,
yeah.
So I understand the argument about running evolution from different sides.
Yeah. Mm-hmm.
But what do you do in the second plot? You start with some sort of a delta function of x?
Well, it's one particle. I mean, this is a discrete system here. You start out with one particle and just at this at x.
And you still, what is that? Why do you still have this?
Well, that's to remind me.
Just to remind you of the plot.
It's to remind you. It's just to remind you. It's because that's the way.
Yeah, it's a point to measure. You measure everything from the left on that.
Right. You have to, the spread should cross that line for T of x and T
What's confusing me also, why do you say it's to the left instead of the right?
Well, because I happen to put this guy to the right and this guy to the left. See, if I'm doing this, there's nothing, and the first way of doing the FKP equation, there's nothing interesting that happens to the left here, right? It's just T is 1 all the time. And if I evolve this, what's interesting is what happens to the right. So I have to, then if I start over here with this, then what's interesting is what happens to the left, because obviously going to the right here doesn't do anything. It's not related to it. It's like when you do the dipole evolution, we presume that you're starting out with a dipole much smaller than the McLaren-Vanderbilt inverse saturation momentum, and we evolve it. Now, if we look for smaller and smaller dipoles in that evolution, that's not interesting. They're not going to ever scatter on the McLaren-Vanderbilt nucleus.
Isn't the same discussion applying also to the BMS equation, where you have splitting dipoles and dipoles in the time-like evolutions, and then you ask what's the probability for them to get outside a given angle?
You bet. You bet. You bet. You bet. Okay, that's the first thing I wanted to give. As I say, I think this is very intuitive, but you'll see how I'm going to use this, and you will see how I'm going to use this. And this is really to sort of help you if.
So question. So what is how should I think of the nonlinearity, the nonlinear term in the equation? Probably. Sorry, but in this branching random walk picture, somehow you have diffusion and the branching, those are linear, but is the nonlinearity somehow
there is no nonlinearity.
So why is there a nonlinear term in the equation? The way I think of it, the nonlinear term is that it stops t from becoming larger than 1.
You're right.
So is it somehow should I somehow in this branching random walk picture think of it as related to the fact that you're looking at the probability that one or more particles are to the left of x equals 0. So somehow the t squared corrects for the double counting if many particles diffuse to the left of x equals 0.
I don't think it's that simple. I don't think it's that simple. I can give you the way. One way of doing it is that suppose we've done this. We've evolved up over some large period of time, and now let's try and go back. Try and start to go backwards by delta t step by delta t step. See, this was a deterministic evolution, this part here. So we can now evolve backwards by one step. And so this whole curve will move slightly backwards. And I think what you can see that it's not too hard to see that if you do at the same time one step backward in this deterministic evolution, and you do one step forward in the evolution of this object, you see when this object multiplies, it is two objects. And then each of those objects will multiply this t. That's the t squared in the equation. But this has nothing to do with unitarity. This is occurring way down in the tip of an equation here. It's nothing to do with, I don't think it's anything to do with unitarity, and I don't see it connected with probability conservation very clearly either. And so the different terms that you have in the evolution here will exactly have the form of evolving the differential equation backward 1 unit. But only after you average over all the different probabilities that this takes. If you do one event here, it won't work out. Because, you know, in that one event over a small period delta t, maybe there won't be any multiplication. Maybe it won't double. So it has to be an average. I must say, I don't have a deep, I find this, you know, in some sense, a little bit mysterious if you view it in the sense of why should there be a nonlinear equation which gives you the probability of an extremely linear process? I don't know. It's extremely linear but stochastic process.
Isn't the same logic as for the fact that the equation for the generating function of a classical branching process is a linear process? The generating function for that imposes probability is not linear. Like the equation of yourself for the dipole. I think that's the same. It is probability conservation. The fact that you branch a particle into two, and both of them have the possibility to do something, the same thing again and again and again.
No, I agree with what you say. I agree with what you say, and it is the same thing as it seems to be very similar to the same thing.
The self-similarity of the branching process.
As the branching.
Each of the two daughter particles can generate their own branching trees.
Yes, so it's certainly very similar, except that in that case, in the generating function, one never does averagings. You have two equations.
Exactly.
Here you see when you do this, you have to sum over lots and lots and lots of events here. You can't use one event. There's sum over many events to take the probability.
This is how you usually derive the decay equation. You did to look at a system involved the dipoles with one dipole, two dipoles, n dipoles with untitled probabilities, and then they scatter all on the target.
I agree. I say from the decay point of view, it's almost obvious. It's almost obvious. You see, if you evolve this thing, you see, this is like a BFK evolution backward. You couldn't use BK evolution. That would be the wrong answer.
No, we have BFL. BFL situation. Is that right?
Okay. Okay. Let me draw. I want to draw this in a picture, which I'll use in a little while. Because this picture is going to be, it's going to appear in the discussion of the diffraction. So I want to draw a picture in the. Now I'm going to draw the QCD version, the Y, and the logarithm of any scale, say x01 squared, u squared. And if you have a Maclaurin then a Goplan nucleus, there's a saturation line that looks something like this. So if you start out with a big nucleus and you evolve it, you find there's a saturation, and that corresponds here to that P point over here. And then at some point, there's Y. You get here and you say, this is all saturation. This is a scaling region here. So I fix a Y and look in various dipole size. That's a scaling region. Then when I go out here, the eigenvalues are changing, and it's what it is. And it's not so interesting for my discussion. Now, when you evolve this way, i.e., going from here to here, this is a saturation line. If I start at a point here, which is like the x here, if I start here and evolve backwards, so if I evolve backwards, I can draw a dotted line, which is sort of, this is the place where there's a probability of having a particle this far to the left is over 1. The saturation momentum comes over here. This is the saturation line for going backwards, starting from, say, x01. And then, you see, if we're down in the tail here, where t is very small, what you have to do is, starting from here, you have to get some fluctuations which bring you over this point. The mean field won't get you there, because then t would be order 1. If the mean field got you there. But if you go deep into the moderately deep into the scaling, you're going to need rare fluctuations. And then this line here is no longer a saturation line for that evolution. Now, if one replaces the evolution, if one replaces the stochastic evolution going backwards by a picture of a boundary and doing deterministic evolution, this plays the role. See, if we evolve upwards in a deterministic way, obviously, if we take that boundary, so if you evolve by a BK equation, you know that you can replace, to a very good extent, the BK equation by a BFKL equation and put in a boundary there, an absorptive boundary. And as far as all the general features of the evolution, that'll give you the same results. It's the same universality class. Therefore, you could evolve backwards, starting at this point in a deterministic equation with this boundary, and you'd also get the same answer because it's a linear equation in each case. In that case, this point plays the role of kind of the farthest out where you allow fluctuations, and it plays the role of the discreteness boundary rather than the unitarity line. So there's a duality between discreteness going back this way and unitarity coming up that way. Okay, I'll come back to this picture at the very end when I derive the diffractive scattering. Let me stop with that now, and let me go on to ancestry. And the Derrida-Mottershaw result. So ancestry. So let me describe in the context of the way Derrida and Mottershaw did, although I didn't quite, this is the problem I'm going to describe the same thing, the problem they wanted to do and the problem they actually did. So their object was, they want to take a branching random walk, follow it over many steps. So like the branching random walk, it's a little bit hard to draw the picture of the diffusion, so I'm not going to try and do that. This is a picture of the branchings. And so particles split and they diffuse, so they move around. And this goes on for many, many, many steps. And then at some point, you stop this branching random walk, and you can ask a number of different questions. So, for example, you can pick out, one could pick out, say, two random points. You pick out this point here, and you pick out this point here. And you say, what's the nearest, the last common ancestor? And so if the X is the last common ancestor, would be this point here. But if I chose, say, this point here, and I chose, say, this point here, then I'd have to look back and back and back, and I'd find that was over here. So the ancestry problem is take something like a branching random walk, evolve it over many, many, many steps, have some rule for particles that you pick at the end. It could be two arbitrary particles. It could be the two particles furthest to the right. It could be the K particles furthest to the right, or in a particular Derrida and Mottershaw do for much of their papers, they weight all of these particles by a Boltzmann factor. And then they ask what's the common, they choose the particle by a Boltzmann factor. So give them a probability of taking a particular particle. And then they ask what's then the last common ancestor, i.e., if you start out at time equals 0 and time t, it's a question of at what time was the closest common ancestor, closest in a sense of working back from t, at what time the closest common ancestor happened. But they couldn't do that problem. So what they did was they did another problem which they could do analytically. It's a problem of it's a model that's used in spin glasses, and it's called GREB model. It's a generalized random energy model, and roughly what it does, instead of having one particle break into two, one particle breaks into a large number of particles. But then you continue that process over a very large time so that the total number of particles is much, much, much greater than that very large number of particles that came out of each step. That very large number of particles that comes out of one step cuts down the stochasticity because there's a self-average that's going on at each step, and makes it possible to do the problem analytically. They then claim that general features of that model should be the same as a random, as a branching random walk. And let me state the result they had. So I'll state that they state many, many different things that they evaluate. Let me take one particular thing. At time t, pick the k particles rightmost.
Sorry, what does right and left mean?
Well, you're starting out at 0 here, and things
So
go to the left and they go to the right.
There is some x-axis.
Yeah. This is a one-dimensional model. It's one-dimensional model.
But
Typo size, typo size.
no, I understand neural language, but you mentioned some Boltzmann factors, so there is a.
I'm not going to do that. I'm not going to do that. I'm just.
Okay, so there is some model with
We don't
Boltzmann
have any
factors
Boltzmann.
which we're not, no one
No,
knows
no,
how,
no.
so
That
maybe
Boltzmann factor was a property not of the model but of the measurement. See, the measurement is pick the rightmost k particles. That's the measurement. Another measurement would be to say pick two particles, and the one which they like is that most of the time they say pick particles at t according to a probability of a Boltzmann factor. Now, since I'm not going to do that measurement, I will not comment on it. It had nothing to do with the evolution. Nothing to do with the evolution.
So right now we have no Boltzmann factors, we just pick in the rightmost k particles. In this multiple branching where each step one particle can go into a gazillion.
No, I'm going to describe it in the branching random walk because they did numerical work to show that their GREM model was very close to a branching random walk. They couldn't solve it analytically, but they say numerically they hypothesize that they should give the same results, and then they back up that hypothesis by some numerical simulations. Although they don't solve the branching random walk analytically.
Okay, so the splittings are 1 to 2.
It's really one with branching random walk. So to pick up the rightmost k particles, then the first common ancestor, going back this way, first common ancestor occurs at T0 where, so I'm just going to call where the first common ancestor occurs as T0. And then the probability of finding it at that at a T0 is equal to a constant. They actually calculate this constant too. We're not going to be able to do that. It's a T over T0 over T minus T0 treehouse. So they give a probability of where the first common ancestor will come.
But the probability divergence is equals to 0.
Oh, yes, but you can't look too close to the edges. Yeah, let's say T0, T minus T0 greater than They give a long discussion about what happens at the edges. The problem right near the edges was a problem that was solved much before this problem met. So it's their object was to get this. In our case, not being too close to the edge is going to be large mass diffractive rather than small mass diffractive.
Does it depend on k?
Yes. Yes. There's a constant here which we calculate, but it doesn't depend on k. So, but remember, k should be, you should first choose a number k, fix it, and then let t go very large. If you choose k's bigger and bigger, this asymptotia will come in later and later. But ultimately, for sufficiently large t, there'll be subdominant terms here which will keep
But that temperature for T0 given P of T.
This is the equation, no, excuse me. This is the probability. So this is the probability that the first common ancestor will occur at T0. and it is independent of K for sufficiently large T. I say there's a constant here which is solvable, which they solve for, and it doesn't involve K. It's just involves the properties of the. So it's a constant which is different for Graham and for branch and random walk, but it depends on the nature of the process, but it doesn't depend on the measurement that's made. It just doesn't depend on this K. Okay, it's a it's a curiosity. It's kind of interesting that there is such a simple formula.
And I suppose the number we have depends on the coupling. So the branching probability was 1, and the vertex of the branch was 1, right? Or would that change?
I don't believe. You see the.
Alpha is.
Yeah, they always use scaled equations in which couplings never appear.
Exactly.
And so I'm not sure I remember whether it's really doesn't depend on the coupling. Well, in our case, we may have couplings in there. We can't determine the constant in our case, and we may have coupling events. Yeah, there are. I'm not sure. You see, because this is a true asymptotic thing, sometimes the coupling is very weak. You just get rid of that by evolving it. So we know in QCD, most of the effect is going to be an alpha Y. It's the alpha Y will come in. And that's similar for them. Their T is really kind of that the coupling pulls it into. And so the
definition of the scale time may depend on alpha S, but the exponent may not.
Yes.
And the common ancestor is common to all the K parts.
Yes.
No exceptions.
It's important that they be off to the right. If they were chosen randomly, of course, this wouldn't be true.
So they will sequential.
Yes, this is the rightmost particles. You start from the you do an event, and then you got this gazillion particles. You start out the far right. You count the first K particles in that event, and you search back for that common ancestor, and then you say what is the T0. Then you do it again and again and again and again, and that gives you a probability distribution for the T0 of the first common ancestor for the K particles. It's not. It has to be done on an average way. Okay, let me come to diffraction. I'll come to the physical problem.
You're not going to derive the 3 maps.
I'm going to derive in the QCD context.
Okay.
Yeah. And in this context, Stefan and I have a version. We have a different derivation of their result, in which the 3 comes in exactly the way it does in the QCD case. In their case, the 3 halves. Well, I haven't been able to penetrate their calculation really well enough to understand the 3 halves there. I'm going to do one other sample calculation because that's going to be really important for the diffraction. I want to do a calculation of the total cross section. I'm going to get an answer you all know. I want to calculate so I'm just going to do dipole big nucleus scattering. We imagine that this dipole comes from deep elastics from a virtual photon, and if the virtual photon were longitudinally polarized, then there would be a pretty good correlation between just a generic correlation between the size of the dipole and Q squared of the process. If this were a transversely polarized photon, virtual photon, of course, there wouldn't be a good connection between the dipole size and the Q squared. And then experimentally, to do this discussion, one would have to measure two jets to know what the Q squared was. Because when you do deep inelastic scattering for a transversely polarized virtual photon, you have a complete range of dipole size and a logarithmic integration that comes in. And so you can't say that the dipole is small or not small. For longitudinally polarized photon, the dipole is small, is on the order of the size of 1/2 of the virtual photon. And I think that's a well-known.
You need to adjust for the dipole size measurement of the Q squared.
Yes. See, the thing that's going to correspond to position here size. I want to do, I'm going to do two calculations. First, I'm going to do a calculation of the total cross-section for a dipole on a big nucleus, and the answers you all know, but I'm going to do it in maybe a way that's a little bit different than you're familiar with, and then I'm going to repeat that calculation for diffractive scattering. I'm going to take the ratio and get an answer which will look exactly like this thing here with the corresponding variables. So let me do sigma dipole A in a slightly different way than we're used to. I've talked about this already now, but I want to now really go through it. So this is the logarithm of dipole size x01, and then some scale size mu squared, which isn't too important. I've scattered dipole on a big nucleus, but they're a bit of a popular nucleus. And I want to look now. I want to do make a measurement right over here in this scale. Well, you know that the cross section, so you know, sigma dipole nucleus A proportional to q sub s squared of y x01 squared to the gamma 0 as the logarithm of 1 over q sub s squared of y x01 squared plus some constant. Right? This is the scaling law that goes away from saturation momentum, and x01 squared gets smaller than 1 over qs squared of this y. It goes down as a power, and it goes down to the power of qs squared times x squared. And then it has this logarithmic factor. This is known to be a property of the solution of the decay equation. This is property of the solution of the decay equation. I want to see that form come from the stochastic language, because it has two pieces in it, and these two pieces are sort of the key. If you look back at the Derrida-Motashov method, you can see those two pieces hidden in there, but it's not brought very explicitly. So now, this is from BK. Now, from backward evolution, so we start at this point here. I'm going to draw a line parallel to the saturation line. And this line is really the probability of having, see this particle when it moves backwards this way. So I'm going to involve this dipole here, involve it backwards, and then scatter it off just an MD nucleus. When it moves backward, it creates a front that goes behind it this way. And then this is the average value of the tip of the front, starting out with the particle. It's a line parallel to the original saturation line. And now we said before that you get the total cross section by finding the probability that after this evolution, you find a particle to the right, to the left of dipole size greater than or equal to the inverse mathematical saturation momentum. But now I want to show you, if you look in detail, what are the important fluctuations that do that? And so what happens is this thing starts to evolve. It has a jump. Besides delta 1, this is a front fluctuation. I'll give you probabilities in a moment. It goes down, it follows up parallel to this. This is a front that started here, it jumped to the left here, follows, and at the very end, it carries another jump. This is the delta 2. Delta 1 plus delta 2 is the logarithm of q sub s squared q sub s squared of y times x01 squared. 1 over that. This size, this distance, is the logarithm of order of q x01 squared q sub s squared. This is x01. The logarithm of that. That's the point corresponding to x01. And then the probability of having a front fluctuation. This is the probability of front jumps someplace in its evolution, jumps, L1, is e to the minus gamma 0, delta 1. The probability of a tip fluctuation is at the very end. When a front fluctuation happens, this whole front, this looks like a normal front. It has lots of particles behind it going very rapidly. A tip fluctuation is a fluctuation of a couple of particles. There's nothing behind, there's virtually nothing behind it. The probability of a size delta 2 of a tip fluctuation is the same probability going behind. So the total cross section is given by the probabilities of these two fluctuations, delta 1 to delta 2, a delta function between, well, a step function of delta 1 plus delta 2 minus logarithm of 1 over qs squared of y times x01 squared, and then e to the minus delta 1 plus delta 2 gamma 0. Now, when you do this integration, you have to satisfy the step function. So delta 1 and delta 2 have to be greater than this logarithm, but you're not going to make it much greater because of the exponential suppression. And so you can very easily see that this is, the exponential delta 1 plus delta 2 is going to be just this, delta 1 plus delta is just going to be this logarithm. So power gamma, exponential logarithm power gamma 0. So this is just s squared of y, x0 1 squared, gamma 0, proportional 2. And then you have so the sum delta 1 plus delta 2 is going to be in the order of this. It won't want to get much bigger because of this exponential decrease. But then you can split up this integration into delta 1 and delta 2 separately, and that gives you an extra factor of the logarithm.
Why is there two jumps?
Why is there two jumps? Well, that's the wonderful thing about this. That's a picture. No one said there had to be two jumps.
No, you just did.
I didn't have to. I mean, you don't a priori. You see, it turns out that that's the most efficient way to get. And I'll try to explain it in a little bit. That's the most efficient way to get a particle to the left of some point is by going through these two different fluctuations. Now, a front fluctuation, you've got to move the whole front. You can't do that at a late time because you see, if you remember, suppose you have a front. This backward evolution is a branching random walk type evolution. It's a BK, not a BK, it's a BFKL evolution, and you've got some big thing here. And so you've got a big, and this is a front going like very high. And so how do you move the whole front by some amount? Well, the way you move fronts is you have some fluctuation that comes out here and then builds up his own front and takes over this front. But at late times, this guy gets very, very, very high. He'll sooner or later just come roaring past this little fluctuating and gobble them all up. That's not true in a front built by BK evolution because you cut the top and the front never gets more robust than a certain amount. But in this kind of a front built without cutting off the top, at late times there are so many particles here, you just ultimately will gobble up any evolution. So a significant fluctuation to move the whole front has to occur in fairly early time. And afterwards, you can't move the front. But what you can do is you can send a few particles way out ahead. That's a rare probability. That's not here. So you don't want to do that in the middle of the evolution because you can send particles out ahead. They don't accomplish anything. And later on, they're gobbled up by the front, and you won't see any remnants of them. So you want to do that down at the very end, where just when you do the fluctuation, just like a couple of units of rapidity, a couple of units of alpha y, you send out a front fluctuation which goes over the top. See, I think that's Stefan and that's our picture of all of these. We've talked a lot with Derrida. It's not quite precise enough for him, but he agrees with the general picture that this is the way of fun. This is the way. These are the two major objects in fluctuations of
So
funds.
I'm a bit confused. So the first jump is the front jump.
Yeah.
When you make like a little fluctuation, then it
Yeah,
goes
yeah. So it occurs earlier. So your front is like this now. And then out here, you take a particle out here, and that particle is far enough ahead, he'll set up a new front, which will be ahead of all the particles here.
Okay.
And that's a front fluctuation.
And the tip fluctuation. Then
The tip fluctuation is something at the very end, you send out something way out ahead. Later on, it would disappear, but if you send it out just before you're going to do the scattering, you use that
last minute.
last minute. Oh, by the way,
Surely it's that.
yeah, sure, it's that.
What's the dynamical effect of that small fluctuation? I mean, it is still separated at the time only from the main front.
You see, if you have a tip fluctuation, a front fluctuation comes from a tip fluctuation, which is big enough to create a new front.
So in that case,
So
it's clear.
what happens, as you go look at later on, this guy will start to create his own front, but this guy will start to move up. If this has gone on a late time, that front essentially moves at a constant velocity. This moves at a constant velocity minus 1 over the delta t, 1 over the delta t from the time of the tip to the time you measure later on. So it moves at a slower velocity. And so what it means is you have to make a late time fluctuation dominate, it has to be, the strength has to be, the distance that you start out with has to be proportional to it has to continue here, the velocity is 0. If this is t is t1, and then we look at this at time t, here the velocity is v0. The velocity of this one is v0 minus 1 over t minus t0. It's actually the 3 halves. And this is not true exactly of t1. It's not actually exactly t1, of course. But the velocity is somewhat less than v0. So this starts to catch unless you make it so. No, you integrate this. The integral v dt goes as v0 t minus 1 over square root of t minus 1 over t minus t1. I may not have this quite. May not have the quite. You have to make this out far enough, but I think I don't have this right. I think I may have. Let's see.
But the integral was determined by rho t.
Yes.
The second.
Yes. I'm not getting my factors exactly right. But
If that the small fluctuations, I mean, a small amount of particles crosses the boundary, what does imply in terms of dynamics of the big front which didn't cross the boundary?
Nothing. See, in branching random walks, there's everything is independent of everything else. So when you have this fluctuation, you let it proceed as it wants to proceed, and you let the big front proceed as it wants to proceed. Then it's just a question at late times, does the big front cross over the small jump? And I'm not quite remembering this. The answer is, if you want that to happen late times, you have to do a rather improbable fluctuation. You can always do a fluctuation, but the later that you wait to do it, the less probable it becomes, because you have to go further out to create such a fluctuation. So this formula here is a formula averaged over all the possible times that fluctuation could have happened. It's dominant at the early times, but I don't remember now in detail the argument of exactly how that goes. Okay, non-diffraction. So this is pretty much the end. The picture of diffraction is almost clear now. So that,
Sorry, happens. All right. It's just magnetic. Like we discussed yesterday, it happens if you add at the beginning of each picture, people get used to it.
it needs to be a stronger magnet. Okay, now signal diffraction. So let's see what does a diffractive event look like where the gap is y0. So I'll draw the same picture. I want to start out, so our whole discussion only starts out in the scaling region, so I'm going to do that here. You see the cross section is very small there. You might expect, you see the old Pomeron language here in a diffractive event. That's the big nucleus, and so there'd be multiple Pomerons there, but let me go past that. The old Pomeron language, you'd have a Pomeron, there are two Pomeron exchanges which create the gap. And then one Pomeron exchange to produce a large mass diffraction. So the mass squared here is proportional to e to the y minus y0. And this is a gap of size y0. And the remaining rapidity goes into creating a large mass. And so in the old days of Pomeron language, one always expected diffractive events to be rather small because they were having several Pomeron exchanges rather than a single one. Well, small if you had a momentum transfer. If you didn't have momentum transfer in the Pomeron route 1, these are all comparable except for logs, but there was never a very, you see, this is this very famous object of triple Pomeron coupling. Comes in here. If you're scattering off the nucleus, of course, there'd be many Pomerons coming here and here, and so it wouldn't be just the triple Pomeron coupling. But it's a rather complicated picture, and I don't know that there was ever for scanning on a nucleus. I don't know ever a very definitive answer. Now, after our paper came out, Zhenya Levin and collaborators had a paper in which they reproduced our result by tricky methods. I haven't completely digested what they're doing, but I think it's probably right. I think you can get this answer without doing the discussion we do, but it helps to know what the answer is when you're trying to find it. So I'm going to do the same thing, but now I want to look to see what happens. This was a generic event for a total cross section. Now I want to take something for diffraction. So this is going to be my y0. And so what I'm going to do is start out the same. Start out, evolve backwards, front fluctuation. And then I'm going to take the tip fluctuation at y0. And I'm now explaining why I want to do that. So if there's a tip fluctuation, if the sum of these fluctuations leads at y0, leads to dipoles which are bigger than the inverse saturation momentum at y0, that system will interact very strongly, and 1/2 the time it should scatter elastically on the nucleus. That's the whole key. 1/2 the time, this whole system. Now, these dipoles that are way back here, they're not going to interact at all. They're just going to come out as particles. But the whole system, if it has at least one or more objects which are bigger than the inverse saturation momentum scale of y0, they're going to scatter strongly, because after all, you could imagine the volume of the nucleus up to this point y0. That's deterministic. And so this line is sort of a really exact line for the saturation of the nucleus of Y0. You have one or more particles to the right of that Y0. You're going to have a strong scattering, and you're going to have an elastic scattering, 50% chance elastic scattering for the nucleus up to this point. Right? Because this is the point. If the scattering here is weak, the scattering here is weak, the scattering here is weak, the scattering here is weak. The tip fluctuation happening with the unit of Y0. And so all of a sudden there's a jump. At this point, the scattering becomes strong. So it's at this point that you have a strong scattering, and then the nucleus. Now this is, I think there are two different things you could do. You could sit with the nucleus. I think one could say make it completely coherent, and we can say the nucleus is in a ground state initially, and the nucleus is in a ground state afterwards. I think you can also the same, except for constants. The formula will hold by saying you start out with the nucleus as a ground state, but you allow nuclear excitations of the nucleus. I think either one of those criteria. And maybe it's easier to say it, and since I'm using this picture of the shadow of inelastic events, it's probably easier to say that our criterion for this diffractive scattering, we want to have a mass on the order of y minus y0, and we're going to measure the nucleus to be before the scattering and after the scattering to be in its ground state. And then the scattering review taking place at this point where the scattering is strong, and that means that it's just like when you, in usual case, you have a big nucleus and you send something to the center of it, which you say will always break up the nucleus. There's always the shadow of that in the optic sense, which gives you an elastic cross section. This is the quantum mechanical problem of scattering on a hard sphere where the cross section is 2 pi r squared. So you have a hard sphere, you send a particle in, and then you say it's a hard sphere. The particle comes in, it bounces backwards all the time. But because of that bouncing backwards, in the sense of wave mechanics, it leaves a shadow behind the sphere. That shadow is a 0 in the S matrix for the evolution of the system. For the T matrix, it's 1, and so it gives an additional elastic scattering. And that's the 2 pi r squared, which is greater than geometric. And so this is the same picture we're having here. We say at this point, the particle will scatter. It will have with equal probability a completely inelastic event where the nucleus is badly destroyed, and it'll have another 50% probability the nucleus will remain intact and in its ground state. Let me now calculate the repercussions of that. And I say that then Stefan solved the Projikov-Levitt equations for this problem, and the answer I'm going to give in terms of y minus y0, he's able to demonstrate, and that's in the. There are 2 papers, a long paper and a short paper. I know the discussion, the detailed discussions in the long paper. I think it's in the short one also. So now let me do the calculate the diffraction. I'm going to do d sigma dy. The dy is just picking out the mass squared, and this is y equals y. We get y equals y squared, and this is the whole proportion. So it's I'm going to give this line here. Just name it. We call this x01 of y of min y. So we just calculate the probability that this guy has a fluctuation that comes out and out to some point when I did the total cross section. So it's the probability of having this fluctuation go past y0, q sub s of y0, and so this formula is proportional to q sub s of y0. See, look at this now as a total cross section calculation right here. We're starting from a point which should be right here on its average. So we'll put the probabilities of these fluctuating, and this probably right here. So this is x01 of y. And then it's the probability of having this fluctuation. And that probability of having that fluctuation is working back this way here is let me make sure if I don't head in the right direction, I'm doing this. I won't. That's right. I just have to put a logarithm in there. And that's the logarithm. And now let me divide by the total cross section, because the answer will be simpler that way. And for the total cross section, that we found the answer is q sub s squared of y x0 1 squared gamma 0 and then log of 1 over q sub s squared of y and x0 1 squared. And now I want to write the q sub s squared of write these various things in terms of common factors. So let me write this all in terms of the magnetic open saturation moment. And so this is equal to q sub s squared mv e to the alpha pi of gamma 0 times y0 over alpha y0 to 3/2. That 3/2 is the prefactor that comes in doing a saturation momentum. And the same thing here. Times e to the alpha pi of gamma 0 times y. And then this term right here is x0 1 squared. It involves backwards, so it's got a minus sign in it. So it's e to the minus alpha pi gamma 0 times y minus y0 over and alpha y is 3/2 alpha y minus y0 is 3/2. Now, you see all the exponentials are going to cancel out, numerator and denominator. This is y minus y0, this is y0, it's y, that's the y here. So all the exponentials cancel out. And these logarithms, when you do that replacement, they're of the same size, and so the logarithms cancel out. The only thing, and the the x01, the magnetic open factors cancel out between here and here. And the x01 factors cancel out. If you left simply with alpha y over alpha y0 alpha y minus y0 to 3/2. That 3/2 here is just the prefactor in the saturation momentum, or if you wish, it's the velocity factor it's the velocity factor in the traveling wave that's moving along that line. So the 3/2 is the usual 3/2 that one has in solving a BFDL problem with a boundary, or without the boundary you have 1/2. And so that's the answer. It's you see the answer, not the ancestor. Where is the common ancestor here? Well, this tip fluctuation is one particle or two particles, but in any case, this whole object only has a few particles in it. And so the first common ancestor is either this particle which is going to the left, or several particles went to the left. They emerge from one particle starting here. Asking two particles to separately create tip fluctuation would give the square of the probability of having one particle institute a tip fluctuation. So the first common ancestor is right at this point y0, whether it's actually this one that's gone completely to the left or it was a precursor just before it isn't too important. It's the point at y0, which it happens. And then this funny factor coming in. And this is the, so this is the, if you wish, this is the diffractive cross-section of the total cross-section. This is then directly related to the probability of a diffractive event having a diffractive event with a rapidity gap of y0. And that's it. That's it.
Sorry, I was running around
I know you
talking about the room, but why isn't it stochastic power of gamma naught?
Because there was a gamma naught over here. You see the gamma naughts. Because I wrote it wrong. I just wrote it wrong. I'm sorry. This is, of course, it's going to be 2 over 2 gamma 0. Yeah, I wrote down the velocity factor wrong.
Oh, I see. So that cancels out.
So that remains in the final result too, right?
The gamma naughts go away because the gamma naught here and the gamma naught here cancel each other out, and it becomes just the 3 halves.
Wow.
Yeah. So it's a very simple answer. The claim is that the relative probability, we don't have control of the constant here in contrast to the area calculation. But what we say, this thing, whatever it is, has no y or y0 dependence. So the probability of getting a diffractive event with a gap of size y0 is proportional to this factor. So there's an overall constant, which means we don't calculate the real overall probability of having a diffractive event, but we calculate what the y0 dependence of it is. And it's a very, very simple answer. And then the Korsakoff-Levin equation gives this answer. So Stefan, when he does this numerics, I think when he has alpha y equals 3 or so, he can see with imagination this factor emerging. And when you take alpha y, really a big number way outside the EIC, unfortunately, when you think it's a really big number, this is just a perfect fit to this, the numerical solution to the Korsakoff-Levin equation. And it's visible as already at moderately small y, but with some imagination, you have to kind of know that that's. You plot the two together, you see the trends are the same, but the real detail compared to the shapes really being the same, you see only a large alpha.
So this is the probability of having a PET gap exactly.
Yes, yes, yes. It
will
won't change if you change y0 by a little bit. Of course, this won't change. This is still the varying.
No, what I'm asking is with Zhenya, we had this quantity of which was a more like probability of having a gap, I think less than or equal to.
I think in his last paper, although have you looked at the last paper? He had a paper at the end of June. Well, it's mostly a phenomenology paper. It's with the group of Chileans, including Russian Chileans, of course. and most of it's phenomenology, but there's one part where they rederive this result. I haven't had a chance to really digest it.
I mean, what you're saying is that the most probable gaps are either very small or very large.
Yeah, this breaks down when it gets too small or too large. You see,
but even if they're not extremely small.
No, absolutely,
absolutely.
No, that's right. That's right.
I thought we had this sort of inverse distribution. We had some most probable gap when we were writing.
Numerically or
no.
Stefan went back to look at the old solutions that so Zhenya with I guess maybe Misha and other people, they wrote a whole series of papers back, the order of 2005, 6, 7. There was a whole yeah. I think Misha was a student. Yeah, they had a whole series of papers, and they had a formula for gap size. It didn't look like this at all, Zhenya does not complain about that now. It just wasn't a very detailed numerical calculation.
I guess what I'm thinking is if I just take a triple power on versus
yes.
right?
Yeah.
It seems like the gap probability in that particular bag increases with the size of the gap. Oh.
Yeah.
So how does it square off with your result?
Well, you have to know what to do here.
In the vertex?
Yeah.
Oh, just a local, oh, in the prominent speed, it's just a fact that it's a constant.
Yeah. See, that's, I think, what Virginia has done now, but as I haven't, I think one of the problems in a Pomeron is not a Pomeron is not a Pomeron. If you have Pomeron factorization, and of course it would be very trivial. If you have Pomeron factorization, you put a number in here and just put e to the 2 times alpha minus 1 here and e to the alpha minus 1 here. That would be the full answer. But as you know, when you have a large Q squareds, and after all, this is still large Q squareds in here, the way the Pomeron couples is not a factorized form anymore. And so I don't think it's so easy to know where to put that here. See, this is coming, and we're seeing it very explicitly because the form here of these fluctuations is all the same, but then it's these sub-factors which are giving the velocity of the. See, if you have a fluctuation down way at the very end, for example, then the original evolution and the evolution that starts with here and goes up here are effectively the same because they're both almost over complete rapidity. And that's the statement the y and the y minus y0 cancel, and you just have an alpha of y0 to the 3 halves. And I don't know that you can get that very easily from the Pomeron language.
It's very non-trivial. It is all coming from the pre-asymptotic correction to the QS. So how can you get it from a simple argument?
Right. So you need to, your Pomeron language would have to be sophisticated enough to understand these 3 halves power set.
Right. So to get in a regime where this is a solution, right? This is a geometric scaling regime.
Well, yeah,
that's, I know it's a broad picture, of course.
Numerically, Stefan pushes things, and he, on top of it, instead of the scaling, we stick in the Gaussian that comes as you move along here, and he claims numerically we will see the Gaussian also.
Yeah, the diffusion also.
Yeah, that's right. So in this, really in the scaling region, the diffusion factor is small, it's 1. And he claims to be able to follow to some extent the Gaussian factor.
In theory, to fit the social decay equation very well with the numerical result for the diffusion coefficient. Perfect.
So I mean, typically you have alpha y a few units, that's okay. So here you just need the double interval because you have y and y minus y0. So you need just simply double the units. So,
but could it be also?
No, it's okay.
No, but I'm just saying that maybe when you get when y naught is very small or y minus y naught is very small, then your sort of your formula is not reliable and maybe.
Well, it's clear that, for example, when y minus y naught is not small, this whole picture doesn't make any sense. You haven't formed a front, let alone have it fluctuate twice.
Right.
So that doesn't make any sense at all. Now, when the gap size becomes very big, we should be going, when the gap size becomes very, very small, let's see, so that's when the y0 becomes small. You see this growth, this 3 half growth certainly isn't going to be correct as we go into. Again, these are these are asymptotic terms here. They're asymptotic terms, and so if y0 is small, if not too big, we're certainly not going to believe. Not going to believe this thing here even probably. So we have to be up far enough that we believe the evolution of the evolution starting from the nucleus, and we believe the prefactor, the power of the prefactor. I don't know how big that has to be. The trouble is, I think theoretically, also you say, oh, you need alpha y greater than 1, bigger than 1. Yeah, that's clear. If alpha y is less than 1, you don't have any evolution. So alpha y equals 1 is where the evolution starts. And then presumably you don't need too much. You need a couple steps of evolution for this to set in. And if alpha is a third, so you need y. Well, I think he at alpha y equals 3. He finds that you can see this.
So numerically, she finds this type of behavior.
Even at alpha y equals 3. Even at alpha y equals 3. Right. But to really set in, you need larger. And then you see this shape really, really, really well. It helps with the small alpha y's to put in the Gaussian also. And then it looks a little bit better.
Could be that our end-waving argument is wrong. Because we have the totally opposite. Why not?
Oh, good. I'm glad, because that means it's not so trivial. if you have a physical, if you have a physical picture and it doesn't quite work, that's always nice in a sense because it means that the argument isn't trivial.
So I have a more naive question. You started off with the branching random walk in one dimension.
Yeah.
You've got a diffraction physics which relates to two dimensions, first dimension.
You bet.
So how do those get the same result? I mean, shouldn't I do the VRW in 2 dimensions?
You see, it's this idea that these things, indeed, the branching random walk is a one-dimensional thing. The evolution of a dipole via QCD is a two-dimensional thing, and but they're in the same universality class. I see there's a discussion in Meunier's lectures in the summer school of Wuhan, where he goes through detail and makes this correspondence. It proves it to the same universality class. It's not that they're the same, but the same universality class means that whenever you find a formula like this, it will always look the same. The factors will be different, but the shapes will always be the same. Yeah.
I think the question was a little bit more simple in the sense he says that dipoles have 2 dimensions,
Yeah.
but then it is the logarithm of the dipole size. So basically it is one-dimensional even with dipoles.
Yeah, right.
The angles don't matter. The angles
Don't
don't
matter.
matter.
It's the log of
One
the
takes
size.
the highest energy asymptotics, which is symmetrically angle and variable.
Yeah, the variable here is playing the role of the position in one dimension is the logarithm of the inverse dipole size after that. Yeah. That makes it that you can compare them. The number of variables are the same. As you were saying, there's no the angle doesn't play any role. What do you need to say? Yeah.
So you kind of started. So what exactly defines the universality or the concept of the universality class in this case? I mean, can you be a little more specific, or
Yeah. You see, let me first go back to the dual picture, because the universality class there I think is easier to say intuitively. Say the PK equation and the MZP equation are also said to be in the same universality class. Now, I think what defines that universality class is that you have a linear differential equation in time, linear differential equation, which has a growth term, a diffusion term, and something which is a nonlinear term which limits the growth. And it's a nonlinear equation, 2 fixed points, each of them, with 1 unstable and 1 stable. See, once you have that, so then it's got to kind of all be the same. Now, in this branching random walk, well, you see, if you believe the duality in the pictures, if you take McKean's theorem for the discussion of let me try. The universality class then in the branching random walk, I think what you need is the following. You have an object which stochastically, that means with a certain probability over a certain time interval. Now QCD, the time is alpha y. You have an object which can break into 2 objects. And there should be, either going along with that or separately, something which says that the sizes or the position of the object can change by a finite amount. Now that's the diffusion in the branching random walk. In the dipole case is the fact that the dipole splitting, the 2 dipoles have different sizes. The the most dangerous thing is that splitting should D-splitting should not go too far away from where they start out. In the dipole language, the splitting to large dipoles, it doesn't go very far out. It's suppressed by the cortically by the bigger dipole size. However, in the small dipole, of course, there's a singularity, a logarithmic, there's a very strong probability that a dipole splits into one dipole and a dipole of the same size. And so that potentially breaks the way that the branching random walks look. And as long as we're insensitive to measuring those small dipoles, then that doesn't cause any problem. See, this breaking of a dipole, the one very small dipole and a bigger dipole, if you do a scattering that that's something of which the splitting looks like this. Now, look at a wave function, the probability. Then you take out a probability, which looks like this. So this is the probability of splitting to small dipole. This is taking out that probability. When this dipole gets very small, nothing that we ever do when we use that is going to distinguish this system from this system here. And so those small dipoles all just cancel out in the end, they don't play a role. But it makes the picture of the universality much more complex. I think what Stefan does in his notes is not the branching random walk, it's the FKBP versus the BK. Right. Yeah.
Let me put a phenomenologist hat on.
Oh, okay.
I haven't worn it in a long time, but we have a discussion in week 4 here.
Yes.
For EIC specifically,
Yes.
The argument is that having evolution between, say, y0 and y, so by generating a high mass m squared, is not really necessary. And even for Hera, I guess Cyril would be the first to say that really, for instance, you can describe a lot of Hera diffractive data with m squared, so the stuff you produce being just a QQ bar pair plus a QQ bar pair and then non-identical gluon, and that's what I think.
Bartles had a model with that.
Maybe even Colesberg and Wusthof, right, originally their calculation.
Yeah.
Then when you look at diffraction. So to play devil's advocate, why should, so for EIC should we worry about evolution between y0? So I think it's okay to have evolution in the gap up to y0, right? If the gap is broad enough in the masses. People who looked at the data say are not terribly large to have y minus y0 also too large.
Yeah, no, it's true that these for not too large mass diffraction or small mass diffraction, I mean this was Bartles and various collaborators, Wusthof and others. They had this model, and they had it was a 2-component picture. They had a QQ bar and a QQ bar gluon, and they described in the small to moderate mass diffraction. They described they had good physical data with just those 2 components. I have no complaints with that at all. That's kind of boring.
Well, that's a complaint.
Okay. Yeah. No, I don't know that. As I say, I think this is maybe marginal for EIC. It certainly isn't robust because it needs a fairly large Y0. That's just what you're saying. You don't need all of that stuff for moderate Y0.
More. I'm talking about y minus y0.
I'm sorry, Y minus Y0. Yeah. So
That's
yeah,
what I hear.
I don't know that I don't know how relevant this is going to be at EIC. I would say that the best I would hope for at EIC is you might find a hint. But it's a hard measurement because you either have to do longitudinal photons, or if you do transverse photons, you're going to have to go in and somehow measure jets.
Also diffractive dijet.
Dijet plus garbage.
And a gap.
Yeah, but big mass in addition to the 2 dijets.
And then a gap.
Yeah, because the trigger on the dijet, as I say, as you know, when you have a transverse photon, typically the quark and anti-quark, they have a logarithmic integration in the z variable of the quark and the anti-quark. There's this long range of integration, and that gives the first logarithm in the renormalization group discussion of the structure function. Right? It's this Bjorken called the asymmetric the line jet bond. That aligning of the jets, you see the longitudinal moment fraction is tightly correlated with the transverse momentum and the size. So you're integrating over a wide region of transverse size. The triggering on two jets would be just to pick out the equal splitting of longitudinal momentum and small size. And that's very hard, so it's a very hard measurement. And longitudinal measurements are always very hard for reasons I don't appreciate that. But no one's ever done good longitudinal photon measurements. And now EIC is going to be a much better machine than anyone else has ever done. And the detectors are going to be super. So maybe they can do longitudinal photon. And then you don't have to do any of this because there is the splitting of the photon going to the quark and anti-quark is always on the order of 50%, 50%. There's no logarithm, just small x, and the size is always on the size of the order of 1/2. There's no logarithmic variance here. You're one log less in the evolution of longitudinal structure functions compared to the transverse structure function, and that's what makes the dipole size easy. Then I don't think you have to tag on anything in the final state. You just do a photon measurement. Well, you have to tag on the gaps size, because that's all.
FL diffraction.
FL diffracted.
Okay, so one has to look probably more specifically, because of course the AIC would have smaller error bars in FL.
Bigger error bars in FL.
Bigger than in F2, but smaller than Hera.
Yeah, yes, they should.
But then
They should.
improve
They
as
should.
well.
Yeah.
But
Well, this is the problem with Hera. If you remember, Hera never ran the machine for longitudinal structures until the last couple months. So this was very low priority somehow in Hera running. And then the director only allowed them to run at the point the machine was decided to be turned off. So it was very difficult as Slack. Slack tried hard to measure FL and never did it well. Hera, I think, could have done a better job, but they never were allowed to do it until the very end when the machine was turned off, and then there wasn't too much interest in whatever. So I think EIC might be able to do that well. See, not just for this process, in general, the great advantage of longitudinal structure functions is that you know that the hardness of the process is really Q², where when you do the transfer structure function, the part of the time this could be vector meson dominated.
Yes, so you've been talking with us.
The next talk about the next.
Right, so we're going to reschedule the Anisys talk. So there are two options. One is we can have it at 2:30 in the discussion state. The minus of that situation is discussion room is smaller, so we'll see Crozier. But the advantage of 2:30 is that the other option is 4 o'clock here, but by 4 o'clock many people will be promptly asleep.
Europeans will be certainly asleep by 4
Europeans.
o'clock.
Those guys, everything was
The Anisys will be asleep. I mean,
We'll get him coffee.
For the moment, I don't feel
The discussion. Okay, so let's try to do it at the discussion room. The discussion room, for those of you who don't know, is right behind this wall. What is
The discussion time of 2:30 or
I believe the room is available at
There
the
was no
front.
discussion on the only discussion in the program today. Come on.
There's no discussion in the program. We can have, after the Anisys talk, we can have discussions on whichever topics people feel strongly about. So, other than that, let's reconvene at 2:30 in the discussion room. All right, so.